sorry about the choppy editing, but we do what we can, you know what I'm saying? Okay, so that was 14. What is the difference between a limiting reactant and an excess reactant? A limiting reactant is the thing you're going to run out of first. In this reaction, it's SA. We're going to run out of SA first if it was 100 grams of that. An excess reactant, you saw how my CH4 could produce a lot more of my product. Well, that's excess. Basically, that's not going to get used. It's not going to get turned into product. It's just going to remain in the beaker. Oh my God! What do you want, wife? Jailbreak challenge? Toughest obstacle run the law allows. Okay, well, maybe we'll do that. Okay, you know we like to push ourselves. All right, excess reactant you're not going to run out of. It's just going to sit in the beaker. It's not going to turn into anything. So, number 16, the amount of product formed in lab during a chemical reaction is actual yield. Number 17, the amount of product that could be produced during a chemical reaction based on a calculation, that 3-box calculation is theoretical yield. Okay, and based on number 10, what is the percent yield of the reaction if 6 grams of CH4 is produced? Okay, so this is where I need that up there. So I actually produced 6 grams of CH4. What? Actually produced 6 grams of CH4. It wasn't asking how much CH4. CH4 isn't even a product, but we're going to assume that they mean H2S. Money, I gotta start making 6 grams of H2S, and I theoretically could have gotten 340 grams of H2S. So it's actual over theoretical, times 100, and let's see what we get. 6 divided by 340 times 100, 1.76%. 1.76%. And that number there is my percent yield. Percent yield. And that is how you calculate percent yield. You do actual over theoretical times 100 equals percent. Got it? You don't, rewind it, pause it, whatever you got to do. All right. Time waits for no man, especially not this one. Okay. Now, where are we at? What are we doing? God, look at the size of that gut. Ooh, still got to keep losing. All right. So that's 16 and 17. Yay, we're done with page 1. Percent composition. We got to find the percent composition of Fe and Fe3O4. So, Fe3O4. Well, the first thing we got to do is find out how much the iron weighs. Then we got to find out what the whole thing weighs. And then we got to divide what the iron weighs by the whole thing's weight and multiply it times 100. Or, in terms you can understand, it's molar mass of the element over molar mass of the compound times 100. So let's see. Irons are 55.8. 8 times 3 equals 55.8 times 3 equals 167.4. So the iron is 167.4. And then we're going to add in 4 oxygens plus 4 times 16. We'll get 231. Again, this is element mass, total mass. I keep forgetting the times 100. I don't know why, but I think we're just frazzled at this point. 167.4 divided by 231 times 100. 72.46%. 72. Did I read that right? 0.4, well, we'll call it 47% iron in Fe3O4. Okay, that's number 18. Wow. And then we go to number 14. Okay. And that's sulfur and Al2. Oh, we gotta write this down. This is unruly. Why would they do this to me? Al2, SO4, Al2, SO4, and we've got 3 of these. And they're asking me how much sulfur, percent sulfur. Okay, so let's first figure out how much sulfur we have. I have 3 sulfurs, 3 times that. So 32 times 3 equals. So my sulfur is 96. And then we have to have the whole thing together. So plus, so I have 12 oxygens. 4 times 3 is 12. And I have 2 aluminums, which are, how much? 27 apiece. So my total weight is 342. 96 divided by 342 times 100. 28% equals 28% sulfur. Let's see if she gets the same answer that I do. At this point, who knows? 28%. All right. We're batting 1,000 so far. Far. Yes. Okay. And then we've got 19, 20, 21, 22, which are all identified the empirical formula. Now, what I'm telling you is that if you can factor anything out of the subscripts, then it is not an empirical formula. So this is what I'm going to tell you to do. The cheat is look for even numbers. If they're all even, then I can factor a 2 out, right? So that is not empirical. This has a 3 and a 6 and a 2. There is no correct common factor, so this is my empirical formula. So number 20, I have C2H6, both even. Oh, C1H3, I have CH3. If there's one of anything, that is the empirical formula. So anytime you see that, so number 21, I got C22, H24, O12. Those are all even. C11, H12, O6. 11 is an odd number, so that's obviously empirical. And 22, NO3. NO3, N, 1 atom. You cannot factor anything out of 1 atom, so that is the answer there. Hopefully you'll just look at the key, or come final exam time, you will look and see if they give you 4 things to look at. Can I factor something out of them? You can at least eliminate anything with all even subscripts. And then look at the 2 odd ones and go, oh, is there a common factor amongst those 2? Please don't miss that. All right, determine the empirical formula for a compound that contains 35.98% aluminum and 64. Okay, so what we got is we got aluminum, 35.98%. And I have sulfur, 64.02%. All right, this is the thing that stumps you all because you don't know when to divide by that one number. You're just like, I know I divide by something. You don't know when. All right, so the first thing is we wipe these percentages off and we call them grams. These are now grams of things. The next thing we have to do is convert these to moles. Now, normally I would tell you to do a nice big conversion and do 98 grams and do 1 mole and do aluminum. What is 27 grams? But look, you're dividing. So in order to save room here, I'll leave this up. But what I'm going to do is I'm just going to divide by 27 grams. And that's going to give me moles of aluminum, right? And I'm going to divide sulfur by 32 grams. And that's going to give me moles of sulfur. And I can tell you this already, it's 2. 64 divided by 32.02, or 1. And this one I actually have to go to the calculator. 35.98 divided by 27 equals 1.33. So now I have 2 moles of sulfur and 1.33 moles of aluminum, and this is where y'all get stumped. We're not done yet. You have to divide by the lowest mole total. Divide by 1.33. Divide by 1.33. This is the one part where you all get stumped. So 2 divided by 1.33 equals 1.503, blah, 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 blah. But this is where I can like knock off any extraneous numbers if they're out past the tenths place. I can't ignore them if they're in the tenths place. So I have 1.5 here, and I have 1 here. It's not Al1 sulfur or S1.5. I have to make that into a whole number. The easiest way I know is to multiply it times 2, which gives me 3. But anything I do to that, I have to do to this. Times 2, which equals 2. And so my empirical formula is Al2S3. That is it. That is how you do that. Okay. Hope everybody got that one. How are we looking on time? 11:25. We're going to go another problem at least. At least one more problem. Okay. And then number 24, naphthalene is carbon and hydrogen, blah, 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 blah. The empirical formula is C5H4. And the molecular mass, that means how it actually exists, or molecular formula mass, however you want to say it, is 128.16 grams per mole. Well, the way we find the molecular formula is we take the empirical formula mass, which is, let's see, 5 times 12 is, what, 60, plus 4, 64. So this is 64 grams per mole. We divide our molecular formula mass by our empirical formula mass, 64 grams per mole. And whatever our answer is, in this case it's 2, we multiply times our empirical formula subscript. So 2 times 5 is 10, 2 times 4 is 8. So our molecular formula is this, our empirical formula is this, and that is how we do that. Oh, and now another long one. Okay. Might as well, why not? We signed up for this. Let's do all of them. Yeah, what do we got time-wise? 13? Yeah, we're going to do this one in here. So the first thing they want is for us to determine the empirical formula, and then from there we can determine the molecular formula. They've told us that the molecular mass is 90.04. We're going to divide this by our empirical formula mass, but first we have to figure out what that is. We have 26.76. I'm going to spare you the percentage. At this point, you should know that we're just changing them to grams of carbon. We have 2.21 grams of hydrogen, and we have 71.17 grams of oxygen. Okay, divide this by 12, divide this by 1, divide this by 16, and that's going to give us our mole totals, right? So 26.7 divided by 12 equals 2.225 moles. 225 moles carbon. This is 2.21 moles of hydrogen. And 71.17 divided by 16 equals 4.448. 448 moles of oxygen. Okay, now what do? We divide by the lowest mole total. So it's going to be 2.21, 2.21, 2.21. Without picking up the calculator, I realize this equals 1, this equals 1, and this equals 2. So Our empirical formula is CHO2. Now then, what does that weigh? 12, let's see, 16, 32. 32 plus 12 plus 1, 45. If I divide that, it equals 2. So 2 times that is going to be my molecular. So this is my empirical formula. My molecular formula is going to be C2H2O4. Multiply that 2 times the subscripts, and that is it. Everybody got that? Good. Again, asking y'all stuff you can't answer. Asking you things you can't answer. Okay. Next. What do we got next? Okay. A homogeneous mixture of 2 or more materials is a solution. The universal solvent is water. The substance that does the dissolving is the solvent. The substance that gets dissolved is the solute. The 2 liquids that are soluble in each other is miscible, and a solute that cannot be dissolved in a solvent is insoluble. Hope you all got that. 32. Utilizing the graph. Is 30 grams of NaCl and 100 grams of water unsaturated, saturated, or supersaturated? So really, I mean, I need a chart is what I need. I need something to look at so that you can look at this. I wonder if this is the same chart. Okay, well, let's see. So NaCl 60 degrees. So I'm going to go 60 degrees. And I'm going to go up to NaCl and I'm going to see what it holds. So NaCl at 60 degrees, I think it holds about 40 or close enough. And so they're saying at 30 grams, where are we? Are we under the line, on the line, or over the line? Hopefully by now, and even through this camera from there, you can see that we are way under the line because it holds 40. They said we have 30 in there, so that is unsaturated. It's not holding as much as it can, right? Okay, at what temperature will 50 grams of KCl become saturated in 100 grams of water? So I'm going to go to 50 grams, and I'm going to go to KCl, kind of doing this opposite, and that looks like 80 degrees to me. Hopefully on this one it's the same. 50 grams KCl. Yep. So at 80 degrees, at what temperature? At 80 degrees. I just went to 50 grams, went over to the KCl line, which is this line. And at 80 degrees, that's when it'll hold that much. That's when it's saturated. How many grams of KClO3 can dissolve in 100 grams of water at 90 degrees? So go to 90 degrees, go to KClO3, and it looks to me like, what, about 50 grams? Yeah, I'm going to go with 50 grams. If 25 grams of KClO is dissolved in water at 90 degrees, how many more grams must be added to make make a saturated solution? Well, I just told you that 50 grams is what it'll hold at 90 degrees, right? Well, if I've got 25 in there, how many more can I add? 25 grams. It can hold 50 grams. That's where the saturated line is. Okay. Hopefully all that makes sense to you. I don't think you're going to have a problem with solubility curves. If you do, then yeah, we got greater issues. I wasn't as great a teacher as I thought I was. Oh God, this question again. As solubility increases, I'm going to add something to that. As solubility increases for a solid, what happens to the solubility of a gas? Well, all these are solids, and this is a gas. So what happens to the solubility of a gas? It goes down. Okay, how would you get a solid to dissolve in solution? If given 25 grams of KClO3 and 100 grams of water at 90 degrees, how many more grams must be added to make a saturated solution? We already did that one. It was 25 grams. Okay. What is dissociation? Use Ki as an example. Well, that's pretty easy. Ki is an ionic compound. Ionic compounds dissociate, and they become their common ions. They become their ions. They break apart. This molecule is broken apart. Now, this is not an ionic compound. This is a covalent compound. They're all in the non-metals, right? This does not dissociate. This is a ionic compound. The potassium comes from the left side of the, hello. Hang on.